2 additional extra credit items that are available given the exam distribution. So the first thing is I recognize that's a 521, which is the derivation problem for Chi. So that problem might be too long for this 15-minute exam. So if you tried, you get partial credit for that problem. And on top of that partial credit, I have posted another Canvas assignment that's due later this week. So that's a 10-point problem. So do that problem again, do the 5-1 again, and upload whatever you got onto Canvas. So this time you have unlimited resources you can use, whatever time that works for you. Your TA also went through that problem with you in class yesterday. So just do that again and just try it and upload whatever your answer is. So that 10 extra credit will be on top of the 30 extra credit. So it's gonna be, well, a real extra credit. Just to compensate on we making this exam a little bit too long, all right? So that's one. And secondly, I posted an anonymous survey, basically asking you how the lecture has been going, how the discussion session has been going, what do you feel about the worksheet, what do you feel about the midterm exam. It's anonymous, we don't know what you said, so be straightforward to us and tell us how we're doing and how we can improve for the rest of the quarter. And that's worth another 10 extra credit. That's within that 30 extra credits limit. Okay, and let's see. Yeah, one of the things that I highly recommend you to do is actually learn from your mistake. So I have the tendency of recycle my midterm exam problems that lots of people have missed on my final exam. So just keep that in mind. Let's see, do we have any other questions on the midterm exam before we move on? Nope. Okay, sounds good. So yeah, take advantages of those extra credit opportunities and actually try it yourself, all right? Okay. Other than that, we're ready to come back to talk about entropy. So this is where we left last Wednesday, I remember, before the buffer lecture, where we were talking about calculation of entropy for different processes. We went over isothermal processes, adiabatic processes, and we end here, which is the mixing of different inert perfect gas at constant pressure and temperature. Now this process itself, if you think about it, imagine on the left-hand side, you have a cabin full of gas A, right? So the initial volume for your gas A is VA. On the right side of the cabin, you have gas B, and the initial volume of that gas B is VB. Both of them are of the same temperature and same pressure. And all of a sudden, we remove that wall separating gas A and gas B. And what is going to happen is an irreversible mixing of gas A and gas B with the final volume to be V equals to VA plus VB. So that is the setup for the process. We're talking about an irreversible process, and whenever we have an irreversible process, well, you have to find a reversible pathway so we can calculate the heat transfer along that reversible pathway and then calculate the entropy change for this process. So that's the setup. If you don't have it on your iPad, just take a picture because we are moving on. Now, the few things we want to do. The first step is to set up a hypothetical reversible path. Now, if you think about it, how do we set up a hypothetical reversible path for this irreversible mixing? One of the things you can imagine happening is you have reversible isothermal expansion of both gases to its final volume B. All right, so we start from A here, and now just imagine B doesn't exist, and A expands into this new volume B, which is VA plus VB. And same thing to B, right? So this B expands itself at constant pressure and temperature into its new volume, which is VA plus VB. So that's something that definitely can be done at constant temperature and pressure. It's just the isothermal expansion of the gas into a new volume. And that process can be a reversible process like what we have for the Joule experiment. We just have to take, we just need that process to take place like very, very slowly. So with that in hand, let's think about how to calculate delta S for this hypothetical reversible isothermal expansion of your gas A and gas B. So what do we have here? We're talking about a reversible isothermal expansion. All right, so let's use our A, for example. Or let's put it as our derivative form. So our ds equals to dq ReV divided by T. And in this process, we have it in a closed system, so we can use our first law of thermodynamics, which means we can rewrite this dq ReV to U minus W over T. All right. And you write it out, what we have is this du over T minus, well, actually I don't have the integral yet, so du over T minus dw over T. So here, let's start from the general expression, and then we'll use what we know about the ideal gas in this situation. All right, so generally, if we're considering this process, you have the expression for U to be du over equals to Cv dt. But in this case, we have an isothermal process, so this first term becomes 0. And here for the dw reversible, we have dw reversible equals to negative pdv. Now for a ideal gas, we have pv equals to nRT, and we can rewrite this derivative dw equals to negative nRT over v dB. All right, and then T and T will cancel out. So what we end up having is ds equals to, well, the plus plus cancel out, the T and T cancel out. So we have nR over V dB. All right, and then for this process, let's take the integral on both ends to get delta S equals to nR, well, it's V ln V final minus over V initial. Right. And in this process, we have both gas A and gas B to be considered, so we can write our total delta S equals to delta SA plus delta SB. And we know the initial volume for gas A, initial volume for gas B, and also the final volume, which is V equals to VA plus VB. So write that out. We have, well, number of mole for gas A times gas constant R, ln V final over V initial. So your V final is V, V initial is VA plus B R ln V over VB. All right. So this is one of the demonstrations that these expressions here are general. But when we're working on the red part and also the pink part, now we're talking about a specific situation where you have ideal gas, you have isothermal processes, and some of the terms goes to 0, or you have a different expression for that specific gas. All right, so that's our step 1. now you have our gas starting from its VA or VB. Now both of them are expanded to a final volume V, which equals to VA plus VB. The next one is called a isothermal mixing of expanded gas. So here I'm just showing a figure demonstration in how this process can be a reversible process. It's just like saying, now imagine both of them have been expanded to this final volume V. I know they look smaller than its previous figure V, but here your V are equal, they're expanded to this new volume V. And then what we have is, imagine you have these walls that are movable, and the gas can only pass at a very slow rate. So by moving that wall slowly to the right-hand side, to the middle, you end up having the gas moving into the same chamber if you have. So in this process, we're claiming it to be an isothermal process. So that means we keep both of the chamber at the same temperature. Now you can easily imagine that being done to say if we put this chamber in a constant water bath of some constant temperature. And then the mixing itself is like really, really, really slow. We do not have like a macroscopic force applicable here. So only infinitesimal forces are in play for the process. So we have work equals to 0, and this entire mixing process, well, delta U equals to Q plus W. So delta U is 0, W is 0, so your heat must be 0. And this delta S for the second part of the mixing must equals to 0. All right. So taking together, what is our delta S for the irreversible mixing of ideal gases? Now what we have at the end is, well, delta S equals to NAR ln V over VA plus NB R ln V over VB. This is something we just derived for the first process. And for the second process, your delta S equals to 0. And in here, we can actually have a little bit more information because we have, well, first of all, PV equals to nRT. And also we have our V equals to VA plus VB, right? So using the ideal gas law, you have a connection. What we have is NART over P, right? So that's just using the ideal gas law here to write our VA as a function of NAR and T and P, plus NB RT over P. Now your gas constant, R is a constant, temperature is constant, pressure is constant. What we have is your final volume equals to NA plus NB times RT over P. Or the other way to put it, because what we want is a ratio between your volume and total volume and your VA. Right, so the ratio here, V over VA, thus becomes NA plus NB over NA. And if you recall the definition for mole fraction, which is chi, so here we have 1 over chi A. So your mole fraction chi A equals to NA over N total, right? So now your N total equals NA plus NB. And similarly, V over VB equals to 1 over chi B. And then we can rewrite this entire equation into delta S equals to NAR ln 1 over chi A plus NBR ln 1 over chi B. Right, and normally let's move that 1 over chi A out, so that becomes negative NAR ln chi A minus NBR ln chi B. So remember this one, what's the problem we're talking about? Thus we have the expression for delta S for mixing of perfect gases at constant Tp. All right, so this should be more or less a review. We're using whatever we learned before and apply it to a new scenario. Now, like for example, when we talk about irreversible mixing of ideal gases, it feels like a new problem. But effectively, when we break it down, it's actually an old problem. We're talking about an isothermal expansion of these gases into a new volume. Any questions before we move on? Yes.
So if there's more than two gases, you would add another term?
Yes. So if there's more than two gases, basically if you go back to here, now you have one more term when you write that expression, and that's going to extend. Yes?
Can you explain why pressure is constant?
Well, that's set up. That's given in the problem.
Sorry.
But
Yeah.
even when you do the hypothetical process, it's like the isothermal expansion of both gases, pressure shouldn't be constant there, should it?
This one, we're keeping pressure as a function of volume in this case.
Okay.
Okay? All right. So next up, we will have a little bit less derivation, but a little bit more like conceptual ideas in this lecture. So here, what we want to get is, well, we did all these derivations. One of the things that I regret in my PChem class is I know how to do all the derivation, but I have no idea what entropy means. So I hope this one will fill in a little bit of the gap. So we're trying to introduce what exactly is entropy. We did all these derivations and equations, right? So what exactly is entropy? So let's get started by relating entropy to reversibility and irreversibility and also equilibrium to give you a different way to say the second law of thermodynamics, which is a little bit easier to remember if you, I can't remember that previous statement for the second law of thermodynamics. So hopefully this one will be an easier remember version of the second law of thermodynamics. So let's get started by expanding our thought of delta S from a system, like a specific system, like a gas cylinder, or some random body of water. Now let's expand our way of thinking of entropy from that specific system to the entire universe. We'll start by looking at a reversible process only. So when we're talking about that entire universe, one of the things we can for sure say is, first of all, our universe contains a system and a surrounding, right? So your universe equals the system plus surrounding, or your delta S for the entire universe equals to some random system of choice and the surrounding of that system. So we have delta S of the universe equals to delta S of the system plus delta S of the surrounding. So we'll first look at delta S universe for the reversible process, and then we'll move on to look at irreversible processes. So when we say delta S for reversible processes, we're saying like all heat flows are reversible. I think I have a typo on my annotated note in the previous version. I corrected this morning. And when we're talking about these heat flow being reversible, naturally, whenever we're talking about heat flow, remember, we're always talking about how much heat is being transferred between your system and the surrounding. So what we have is your DS system always equals to negative DS surrounding. Because heat itself is only defined for a process of heat transfer between your system and your surrounding. Now for a reversible process, now what we have, or this one, actually I skipped one step. We're saying is the Q system equals to negative Q surrounding. But naturally you can see because ds equals to dq over T, so at some random temperature, what we have is ds equals to dq system over T plus dq surrounding over T. And these terms have the same magnitude, just different sign, so that must cancel out. Or the take-home message is our ds universe always equals to 0. And as a consequence, if we take the integral of that ds universe, which is 0, we have delta S of the universe equals to 0 for reversible processes. All right, so imagine a universe that only have reversible processes taking place. Your change of entropy will always equal to 0. Okay, with me so far? Then the next one, let's talk about irreversible processes. So this one, again, when we're talking about irreversible processes, let's just imagine a hypothetical cycle. Now it looks like, for example, here from like 3 to 4 is like a contraction in volume, but just keep in mind, this one is just a random picture I put. You can also put it the other way. So we can't get too much information by how I draw this picture. So how do we set this up? Let's imagine a cycle from 1 to 2. That's some irreversible adiabatic process. So that's a process of interest. But since your delta S or ds is not defined for irreversible processes, you have to construct reversible pathways leading to your final way, all right? So what we want to get is from 1 to 2, what we want to get is this adiabatic irreversible process. But in order to have an idea about the nature of the process, we build reversible pathways. So these reversible pathways, we can imagine from like 1 to 2, what we have, I have the arrows the opposite way actually. As for example, it can first undergo a reversible adiabatic process, and then a reversible isothermal process followed by a reversible adiabatic process. So if you remember our entropy figure, you have a random cycle, right? You can always draw adiabats that along those adiabats, your Q is 0. And you can also draw isotherms on that figure where you have the isothermal processes. So here's just one of the random way we connect these points. Now what we know about the system. So in this case, let's get started. So again, if you don't have your iPad and you want to come back to refer to this picture, just take a picture of it. And let's get started by looking at each of the way. First of all, for this entire system, as a state function, your delta system, which means you have your initial state is 1, your final state is 2, that always equals to S2 minus S1. What we're trying to find out is, well, what is that delta of the system? What is that delta S system? So in this case, some of them are pretty straightforward. For example, for your delta S between 1 to 4 and delta S of 3 to 2. So these are adiabatic processes. So naturally, you have Q reversible equals to 0 for this reversible adiabatic processes, and this equals to 0. All right. And then between this 4 to 3, what we have is delta S, use different color. Delta S 4 to 3, that equals to the integral of, well, state 4 to state 3, and dq of the process over t. Let me just write that down, 4 to 3. And in here, our temperature, which I randomly say it's like TH, that equals to, that's a constant for an isothermal process. So let's put it out. And that's TH Q to 4, 4 to 3. All right. So, taking that together, for this entire process, for the cyclic process, when we take the integral of everything in my system for the cyclic process, 1, 2, 3, 4, or 1, 4, 3, 2, I forgot my numbering. But for the cyclic process that returns to state 1, you have it equals to delta S. Let's see. Well, 1 to 4, 1, 4, 3, 2, 1. 1 to 4 plus 3 to 4 to 3. 3 to 2. 2 to 1. 3 to 2. Let's see. 1, 4, 3, 2, 1. Yes. 1, 4, 3, 2, 1. And in these processes, some of the things are null, like this 1 to 4 and 3 to 2 are 0. This one is 0. And 3 to 2, this one is 0. Those are adiabatic processes. Your 4 to 3 is the reversible isothermal process, so we have that equals to your Q4 to 3 over 1 over H, over TH. So naturally, for this process, we have our delta S 2 to 1 equals to negative Q 4 to 3 TH. All right. And then some of the things we can use is, let's use our laws of thermodynamics to get some idea about whether or not this Q4 to 3 is a positive or a negative number. So here we just want to know whether or not it is positive or negative, not of any specific numeric number. So if we use our first law of thermodynamics, what we have is delta U equals to Q plus W, or if you write it in our integral form, that tells you you have the cyclic integral of du equals to cyclic integral of dq and dw. And for this cyclic process, your delta U must equals to 0. And in here, what we have, we just did our cyclic ds of the system, and we find out this one equals 0. And in this process, we only have one of the Q that is not adiabatic. All right, so go back to this process. 1 to 4 is adiabatic, reversible. 3 to 2 is reversible, not adiabatic. 1 to 2 is irreversible, adiabatic. Now, the only thing that is not reversible, not adiabatic, is between 4 and 3. Or that is our Q 4 to 3. All right, so let's write that down. And here, the cyclic integral of work just gives you the total work for this cycle. Or the other way to put it is we have Q 4 to 3 plus W equals to 0, or your work equals to negative Q 3 to 4. Yeah.
Is it supposed to be 4 to 3?
Oh, yeah. So on my annotated note, I was running the cycle backwards. So you can check that out. It gives you the same conclusion. It just we're running the cycle backwards. Nevertheless, thank you for pointing that out. Okay, now our question becomes, what do we know about the sign of the heat 3 to 4? So here, the only thing we have is this process. You have the work equals to negative Q 4 to 3, or 3 to 4. And remember, in our second law of thermodynamics, what we know is the sole purpose of a cyclic process cannot be transferred 100% of the heat, which means random molecular energy, into ordered energy output like work. So that tells us in this process, if our heat is a positive number, means our cycle takes energy as heat and output all of its energy as work. But that violates the second law of thermodynamics. Okay, so spend a little bit of time and think about it. So in this process, why we're saying like Q4 to 3 cannot be a positive number? Because these two terms are equal. Your work equals to negative Q4 to 3 or 3 to 4. So if that heat is a positive number, it means the only thing happening in this entire cycle is we're transferring that heat into some form of work. And the second law of thermodynamics tells us you cannot transfer all the heat, which are random disordered molecular energy, into ordered molecular energy, which are work. So using the second law of thermodynamics, what we end up getting is that this Q 3 to 4 must be a negative number. And recall what we just derived, delta S 1 to 2, 2 to 1 or 1 to 2, let me see. 2 to 1, yes. 2 to 1 equals to negative Q 4 to 3, sorry. Over T. So this is something we derived here. So now we have two pieces of information. We have Q 4 to 3 must be a negative number. And in front of here, we also have a negative for our irreversible adiabatic process between your state 1 and 2. Now this delta S for the irreversible process must be a positive number. Okay? So we're not doing anything like actual calculation or numeric, but the take-home message here is for this irreversible adiabatic process in a closed system, we have our delta S is larger than 0 for this irreversible process. Or if we write it out, we have delta S system, well, delta S 1 to 2 is positive for this irreversible process in a closed system. And it must be adiabatic. what we have is we start from the adiabatic irreversible process in a closed system. And we build a cycle along that process, like a reversible cycle that contains 2 adiabatic reversible process and 1 isothermal reversible process. And by building that cycle and using our laws of thermodynamics, we end up knowing this irreversible adiabatic process of a closed system. You have delta S must be a positive number. Now, this one is a very specific conclusion, but can we generalize it? For example, when we're talking about an adiabatic and closed system, recall what is the definition of an isolated system. So for an isolated system, it is separated from its surrounding by adiabatic walls and no material exchange and no heat exchange. So by definition, when we say something is adiabatic and in a closed system, what we're saying is this is a delta S of a isolated system. It's always positive. Okay? And now, if you think about an isolated system, our entire universe, you can consider it as a big isolated system. So, naturally, what we have is delta S of the entire universe. It's always larger than 0 for irreversible processes. All right, so within the universe, you can divide that isolated system into like closed system, open system, et cetera, et cetera. But what we're saying is we're considering the entire universe as a big isolated system. Well, then for any irreversible process in the universe, you have delta S always going larger than 0. Okay, so let's revisit the second law of thermodynamics. Now what we have delta S of the universe equals to 0 for reversible processes. Delta S of the universe larger than 0 for irreversible processes. So effectively, what we're saying is delta S of your universe is always larger or equal to 0, which is generally true for any process you have in mind. Okay, so that's the simpler version of the second law of thermodynamics that we paved our way through this entire process. So that's why people say the second law of thermodynamics basically tells you the entropy in the universe always increase. All right, so that's a rephrase of the second law of thermodynamics. So I hope this is a little bit linked to what we discussed before on our previous 2 statements of the second law of thermodynamics. And you can use this one to prove the previous one, or the previous one to prove this one. They're the same claim of the same law. They're different claim of the same law. Any questions before we move on? Nope? Okay. And then as chemists, there's always one of the things that we want to think about is how is entropy related to chemical equilibrium, or in this case, thermodynamic equilibrium. So when we're talking about entropy, what we have, remember, if we plot entropy as time, that time can be replaced to like a reaction coordinate or like something that's changing. If you think about it, what we know is that at this maximum point, we're talking about the change of entropy equals to 0 for reversible processes. And at equilibrium, you only have infinitesimal changes of different states. whether it's like temperature change or it's a chemical reaction. So at equilibrium, you only have infinitesimal changes. So that tells us our delta S equals to 0 at equilibrium. All right. And what about before equilibrium? Now, if you have a chemical reaction, or like what we had before, right, mixing of two ideal gases, so before that system reaches the equilibrium, your delta S always, your ds is always increasing. So if we look at the slope here, right, so ds is the slope of this entropy curve. You have ds larger than 0 for irreversible processes. Prior to equilibrium. And now we want to use what we learned from the second law of thermodynamics, from the entropy, to go back and give a new definition to our equilibrium. So when we have thermodynamic equilibrium in an isolated system, we're just saying the thermodynamic equilibrium in this isolated system is reached when the system's entropy is maximized. So the change of your entropy, your ds, is always positive before we reach equilibrium in that isolated system. Now, the other way to think about it is, our universe right now, has it reached equilibrium? So no, right? So your entropy is always changing. We still have irreversible processes taking place in the universe. Okay, today's lecture is more conceptual. It's a little bit lighter on the derivation. So really try to follow our logic and get a little bit of the understanding on the actual meaning of entropy, equilibrium, and these terms. And then we have about 8 minutes. I don't think I can finish, but I can at least get started by talking about the physical meaning of entropy. So one of the questions I always get is like, why we're studying these thermodynamic laws and what exactly we're doing here. So first of all, we use the thermodynamic laws to give us state functions. And then we use these state functions to find out or to predict how materials or molecules or things gonna behave. So for example, we have the zeros law, which gives us the state function of temperature. So remember, the zeros law is telling us like two systems that are in thermal equilibrium with a third system must be in thermal equilibrium with each other. Or the other way to put it, well, if you have two systems of the same temperature as your third system, then your two systems have the same temperature. And then in our first law of thermodynamics, it says there exists an extensive state function, E, so that any process in a closed system is conserved. So we have delta E equals to heat and work, the plus of heat and work for a closed system. And your delta E of the system plus delta E of the surrounding always conserved to be 0. And in thermodynamics, in this class, normally we're looking at systems that are at rest, does not have any external field, so that we have our internal energy. So delta U equals to delta E in absence of external field and at rest. And that external field can be a gravitational field, that's how our pen drops, or it can be an electricity field or magnetic field. But here we're just saying, like, assuming there's no external field, your delta U equals delta E for a system that's at rest. So, and from U, we also defined our enthalpy H equals to U plus PV. Right, so here we have several state functions that's related to the first law of thermodynamics. And at the end, we pretty much finished our discussion on entropy. So from the second law of thermodynamics, we defined a new state function, which is entropy S. So the definition of S is ds equals to dq reversible over T. And the second law of thermodynamics also tells us the overall entropy change in the entire universe must be larger than or equal to 0. So we have 4 more minutes. I don't want to get started with the lecture, but I want you to think a little bit. I will raise some questions for you to think about. So this is the diagram we just finished talking about, right? So we have entropy is maximized at equilibrium, or in the other word, equilibrium is defined by entropy maximized at that point. And before equilibrium, your entropy change, or delta S, is always larger than 0. Now, when we talk about the physical meaning of entropy, you want to think about it on top of entropy, right? We know entropy is maximized at equilibrium. What else is maximized at equilibrium? So you can use our same example of mixing 2 perfect gases together at constant T and P. So we went over that today. Just think about it. What are the things we know? Like, for example, we know that perfect gases molecules do not interact with each other. The motions of these gas molecules are completely random. So it can move to anywhere it like. There's no control over there. And also think about it. Why mixing of gases are irreversible? What makes that process irreversible? Now you just have 2 cylinders of gas mixing together. Or the other way to put it, right now we have our oxygen and nitrogen evenly distributed in air, right? So why oxygen won't all of a sudden move to that corner of the room and we all suffocate? Think about it, why that is the case. And we'll go over that derivation and introduce a little bit of statistical mechanics in our next lecture. Just a little bit. We won't go very deep into statistical mechanics. Okay.